All right. So I'm Dr. Krozik back for another lecture on this time mind and machines. And I am a cognitive neuroscientist, and I have worked with computer scientists over the years on things like machine learning approaches. I often teach for a cognitive science program as well. So I'm guest lecturing for this particular topic. And this is related to these two topics that are intertwined, how we understand the mind through cognitive psychology. We'll start with that, and then we'll move into applications of machine learning and artificial intelligence. So, in light of the history, one of the first points that we start to see cognitive psychology coming up is with Noam Chomsky, and he does appear in the chapter as well. And this was a transition point from the previous period, which had been dominated by artificial intelligence, that would have really had a language created, by the behaviorist method, and that is the way machine learning tends to work. It is very much like a behaviorist function. And then later, cognitive psychology would inform kind of systems design, which would percolate into artificial intelligence later, making the capabilities much greater, actually, than one would get with purely a behaviorist reinforcement function. So B.F. Skinner is familiar to you, and he had taken behaviorism really as far as it could have gone without starting to explain some of the more advanced sorts of reasoning or systematic narrative and language that humans use. He had attempted to explain that sort of thing with his language book from 1957. And the claim there was that essentially all language is just learned by reinforcement. So that you imagine an infant makes a noise, and the parents either give it a noise of approval or they say no, no. And through that shaping process, you see children move to 2 and 3 word statements, and then ultimately hundreds and then thousands of words. That didn't seem quite right to all of the scholars of the day. And it seemed like that would be an awful lot of work by the parents, and it didn't quite seem to fit with what really goes on because children between ages 2 and 3 acquire just hundreds and hundreds of words, and oftentimes there isn't necessarily even an adult around paying attention to reinforcement. The child is just observing and learning through that. So Noam Chomsky is pictured below, and he is famous largely as a linguist, but also as a political commentator nowadays. But back in the 1950s, he was making this claim that behaviorism couldn't really explain the novelty of language. So a statement there is sophomores are limiculous. That would mean mud dwelling. That's a ridiculous statement. There would be nobody that would ever reinforce that statement, and no one ever says that. And so that was just a simple example that you really can't get there all by reinforcement learning because it just doesn't seem to occur that way. Around that same time, George Miller had put together a conference at MIT, and it was sort of the beginning of what we think of as cognitive psychology, and this is dated to 1956. And what cognitive psychology included was this information processing approach. And this is familiar to cognitive science and to artificial intelligence as well. It's like the mind and a computer have commonalities. And there is an analogy here that a mental process can be understood in terms of its similarity to the way a computer operates. And furthermore, a mental process could be understood as an information processing stream through a system that's going in a step-by-step way. And an example of this would be the Atkinson-Shiffrin model of memory from the 1960s. And this would be the type of thing that early cognitive psychologists were up to, which is quite different than what reinforcement learning behaviorists were up to. Notice the similarity here in this model to a schematic that you would have for a computer system. External input comes in through the senses, and it is retained initially by what's known as sensory memory. And experiments had told us around this time that there were two forms of this, one being iconic memory, which is memory that's very brief for visual inputs, and the other being known as echoic memory, which is like an after image of a sound. And so sensory memory's characteristics are that it's incredibly short-lived and it's lost almost immediately. So this is the kind of memory that sticks around for only a second or two, and it's constantly being overwritten. So the external inputs hit our system through sensory memory. They can be lost, or in some cases, they can move on to short-term memory. And that would be the kind of memory that you use for remembering a phone number. You can rehearse it. You can rehearse the digits and then put them into your phone, and then you promptly forget them. So a lot of what we think about consciously would be in short-term memory, and a lot of it is lost. Now, in some cases, it will move on to what we think of as long-term memory if it's a really important thing. And long-term memory can stick around for a much longer time. You don't have to actively rehearse it like you do with short-term memory. So these were differences that the psychologists of the day, mostly in the 1960s, but this model was prevalent into the 1970s as well. They were focused on the different characteristics of these memory systems as if they were separate storage systems like you would have within a computer. Sensory memory had a very short duration, short-term memory a longer duration, but still not all that long, and long-term memory an almost indefinite duration. And there seemed to be a possibility that you lose memories, but you can also recall long-term memories and bring them back into consciousness, and that would happen by going back into short-term memory. So this is a theory, but it's very much inspired by the way information gets processed through a machine-like sort of interface within the mind. And another good example of memory research by cognitive psychologists occurred with Herb Simon's work from the 1970s. They were interested in memory for chess. So it was evident that people were capable of these very elaborated kinds of memory, like remembering everything on a chessboard, provided they're an expert. And that would be the kind of thing where long-term memory is helping you to do what would otherwise be a short-term memory task. So in this experiment, they had people view a chessboard. You can imagine this individual here looks at the chessboard over here, and then a partition is put up, and then he would have to attempt to rebuild the board using another chess set that's on the other side there. And so every time he attempted that by looking at it for 5 seconds and then going back to the board and trying to get it right, that was a trial. That counted as a single trial. So these are the data from their experiment. And you'll notice that it's the amount of correct pieces that's shown on the y-axis over here for chess games. And you have the number of trials it would have taken in order to advance to those numbers of pieces. And you'll also notice that there are three different levels of skill. There are beginners who are shown here, and they're pretty much limited to four, maybe five items at a time. And so they're kind of going in a linear fashion, learning, um, you know, just kind of grabbing learned sets of pieces for 5 seconds and then rebuilding them. And it takes them a good 7 trials to get up to 24 items. Meanwhile, as expertise rises, so mid-level players have an advantage. They have about 8 to 9 items per trial. And then really good experts who are shown up here, master level players, can do this in 4 trials. And you notice they're well exceeding the short-term memory limit of 7 items or thereabouts, or 5 items. They can get up to 16 at a time. Now, the other interesting thing they did in this study was they had rearranged these chessboards so that they're not real chess games, but rather just any old pieces anywhere that would not occur in a game. And that neutralized the advantage. So this is the random board arrangement. And you can see here that the data show a very different trend where nobody really has an advantage. If anything, the experts look sort of worse. They're only getting about 2 to 4 items per turn. And meanwhile, the mid-levels and the novices are kind of just chugging along with their short-term memory. So this tells us a lot about the way the mind would be working. For Herb Simon and his his colleague here running this study, they would think that the long-term memory box would be storing experts' chess knowledge. And then for those of us that aren't chess experts, we have to do the whole task with short-term memory. And you can erase the influence of long-term memory by scrambling up the board and forcing experts to do random boards, at which point they default to this same kind of memory. So the big point here is not so much that we can study chess, but rather that we seem to have models in our heads in long-term memory that can be used in order to process things. This is Philip Johnson Laird, who came along in he was very active in the 1970s and into the 1980s and 90s on mental models, these sorts of ways that we can solve spatial problems. And for Johnson Laird, he had a theory that again looks very much like a computer diagram with different capabilities represented by different rectangles and then kind of a flow chart. And so for him, mental representations can take on three different forms, one being a language-like prepositional representation, another being a point of view, perceptual sort of snapshot, mental imagery, and then something in the middle, which is the mental model, which would be kind of an analogy to the real world, and that this was a continuum. You could sort of store these in many ways. And this makes sense of a lot of the data coming in from, for example, that chess study. Those that are novices would have to use mental imagery a lot, whereas somebody who is more of an expert would be able to augment their memory through this prepositional representation, which is more language-like. Interestingly, I have talked to expert chess players over the years, and they do say that they no longer really think in images at a certain point. They actually think in mental models that are a bit more language-like. So very much the kind of thing that Johnson Laird was talking about. And this divides up the mind into these separate capabilities. Again, this is a real evolution from the behaviorist period where everything would be just one learning system that's aimed at every problem. Now we have multiple learning systems that resemble something you would see for an information processing computer. In the 1980s, we move into a period where cognitive modeling got more explicit. And by explicit, they would actually be running computer simulations on these theories. And pictured here is David Rumelhart on the left and Jay McClelland on the right. Jay McClelland is still around and active, but very senior. And these two had developed what's known as the parallel distributed processing approach. And this helped to really move cognitive psychology more toward artificial intelligence. And parallel distributed processing is not only true of computers, it can also be true of minds and brains. So their original references were from the mid 1980s, and they released software to enable researchers to create these models using these sorts of principles. So a parallel distributed processing model had primitive processors. It ran binary code. Things could either be on or off, excitatory or inhibitory. These processors would be stacked up in layers, and this is what we call a layer even now. You have multiple layers within a machine learning algorithm, and the layers are connected. That's really critical. And then it's kind of like an energy is transmitted through those connections, and iterations can occur to allow learning. These are exactly the same principles that you see within brains. So we know that brains have primitive processors in the form of neurons that can be active or quiet, excitatory or inhibitory influences. We know that brains have cortical layers that are stacked together. So some neurons will do similar things across a layer, and there's immense connectivity through axons. Energy would be equivalent to a neural impulse, an action potential, and the iterations idea would be true of a learning system. So these sorts of neurons proposed by Donald Hebb, so-called Hebbian learning, is updating the weights or the strength of a synapse. or a neural connection within the brain. So parallel distributed processing was true both in silicon form, as these models would be run in the 1980s and 90s, but also in actual biological form in our brains. And here's a nice example of just what they meant by the layers and the connectivity. So you would have an input layer here, and this is a model that's programmed to recognize words. And word recognition seems complex. Language is a very elusive and difficult ability to characterize. But in the form of these models, you could make it very simple. You just have line detectors or edge detectors, and we know those exist actually within the visual cortex. And then they pass activity, either excitatory or inhibitory, depending on the connection. This little guy here would excite the S because it has the crossbar, but it is not present within the T, so it would send an inhibitory influence to that. And then the letter level would be another layer, the hidden layer. And modern machine learning algorithms will have numerous hidden layers in order to allow recognition of increasingly sophisticated forms. And some models do better with a few hidden layers, some do better with more hidden layers. It really just depends on what you're trying to make the model do. And then the output layer would be actual words, and it has the same principle. So the little S node would be excitatory to really nothing because there's no S's. So it's going to inhibit all of these things. The G is also inhibitory, but look at the T. There's many instances where the T would appear and it would have excitatory influence there. So out of this, you would get updates, and eventually the model would settle on whatever word best fit the inputs, and that would be the output layer. So this kind of processing went on not only through the 60s and 70s, but eventually those sort of box models like the Atkinson-Shiffrin would move on to become computer simulations, PDP models in the 1980s, 1990s, as well as mathematical models that could be created to solve different problems. And we see this all over the tech industry now. It really doesn't even need to be pointed out. Everything that's a machine learning approach or an AI approach is going to make use of this. And now machines can learn in what they call an unsupervised way. You don't need a person curating these levels. You can just have a person give inputs in the form of a data set, and then the machines will run through their process, their hidden layers, and they will output an accuracy level. And so that's the sort of power that we're seeing in computing today. This is the field of cognitive science as well, and we offer a cognitive science major, as do most universities. And cognitive science tends to blend this cognitive psychology approach with neuroscience, anthropology, computer science, and other fields in engineering and linguistics to create an integrated approach that gets us toward understanding not only how machines think and learn, but also how the human mind operates at the same time. And we can look for ways that they can be complementary. I think when we get into the actual in artificial intelligence topic, you're often trying to model a mind separate from humans. And this is a little bit of a different exercise than what cognitive psychology was up to. Cognitive psychologists would try to understand how the human mind works, and they would use models and principles and theories to do that. With artificial intelligence, it's often really just the goal is to produce some kind of behavior, a goal-directed behavior, and you want to do it efficiently. You don't want to necessarily build in a clunky emotional system or put in all sorts of inputs and outputs that control the body, right? You're essentially just trying to get answers from a box. And so human and animal cognition is not always efficient, and it's not always accurate. And so sometimes AI is actually going to seek to produce a better answer and a quicker answer, a more parsimonious answer than what a person can do. Okay, so how do we get to that point? It's worth discussing some of the history of how computers developed. And this is occurring really in tandem with cognitive psychology. In the behaviorist era, everything was just a learning system. And then gradually, we moved into this sort of multi-component sort of model. And that was really occurring historically in the 20th century as well. Early computers were using something called a vacuum tube, and that's depicted here. It's rather large and it's a bit like a light bulb. And what a vacuum tube could do is a binary process. It could basically have an on or an off state. That was large and produced a lot of heat. In the 1970s, we moved to transistors, which were still relatively large. They weren't vastly smaller than the vacuum tube, but they were much smaller and they did the same job as a vacuum tube. And then came the microchip, which grew in prevalence in the 1970s, the 80s, 90s through today. The original microchips looked like this, and they would basically be equivalent to a lot of the transistors. So you could embed many, many transistors within a silicon chip and have a lot of binary processors available. And now chips have gotten very, very tiny. So just to give you a sense of the vast development from the 1950s to today, um, a vacuum tube could do some binary processing that was equivalent to the transistor. The transistor was simply cooler to run and smaller, and you could stack them up on a board. When chips came along, it was dramatic. There's 2,000 transistors in one of these somewhat large chips of the day. And in this tiny, tiny modern chip, that's equal to 30 million of these guys. So just vast, vast hardware improvements to enable massive binary processing. And that's why we have all these glorious algorithms that can do useful things within our lives. It's that ability to process in binary with tiny, tiny chips, and why our smartphones are so much more powerful than very old computers. And here is that difference in a sort of vivid format. We have old computers that would occupy rooms with administrators, and you would have to have people seated at desks monitoring these very heat-intensive systems, very sizable systems. This is the original Apple computer from 1970s out in Silicon Valley. And this is actually a wooden cabinet that they put it into. And Steve Wozniak was capable of doing a lot of stacking of these chips in order to get surprisingly sophisticated behavior. And so this led to that sort of personal computer industry, circa 1980s or 90s. It was a big box sitting on a desk still. And then, of course, now through downsizing, just making smaller and smaller components that did more and more processing, we get to the tablet and smartphone era. And artificial intelligence has this promise of outperforming people, and that we could have a smart car that never gets in accidents and drives really efficiently and is incredibly optimized. And it's really that exponential growth in computing abilities that may allow that possibility. And notice that smart cars have been on the road. They generally are very safe, but we don't often all have self-driving cars at this point in history. We have driver assist cars that can add braking at times and use sensors in order to help the driver out, but it's not replacing the driver at this point. Okay, let's get back to chess. This was certainly an interesting bit of cognitive psychology, that you would have people who could have a big advantage due to expertise. And since really the 1970s, as soon as computers became available, there would be the question of, could computers outthink a person in terms of you know the top expert. And if you remember the Chase and Simon study, it had those in-game chessboards and scrambled chessboards, and it had the novices and experts. And the experts showed that big advantage, but only for in-game boards, real chess situations that they learned. And this was one of those studies that you could look at and point to the way in which a computer would solve chess versus a person. Now, this is thought of as adversarial reasoning. It's two beings, two minds going against each other, two humans most of the time, but also human against computer. The human would have an advantage with that sort of stored memory over the algorithm method. So, what the algorithm method would be is analyze all possible moves. That's what a computer would do originally in chess thinking. Whereas heuristics would have this sort of efficiency of analyzing best case scenarios, and then you minimize time spent on probably dead end scenarios. And this was an arms race between humans and machines. Most of the time, the heuristic approach of humans, taking the shortcuts, would be more effective than the algorithm approach when algorithms had limitations. But in the 1990s, Deep Blue by IBM famously defeats Garry Kasparov, who was the top human champion at the time, grandmaster, amazingly accomplished player. And it did take many years before computers could reliably defeat the human expert. So that was 1997, where Kasparov loses. Let's briefly pause the lecture and just watch a little bit of footage on this legendary sort of moment for AI.
This was suspense beyond anything the world of chess had ever known. Garry Kasparov, 34 years old, a cheerful and confident player throughout a dominating career, hovered over his pieces in the deciding game of a match with an implacable challenger. Deep Blue, a computer. Kasparov won the first game in a breeze, but the next day he got the shock of his life. To Kasparov, Deep Blue played the second game much more strongly, differently. Unlike a computer, he said. Kasparov conceded, and the loss wore on his mind for the rest of the match. In each of the next three games, the world's preeminent chess players, man and machine, battled each other to a draw. Kasparov's early scorn for Deep Blue's abilities had proven a great mistake. In the final game, the computer led with the white pieces, and soon Kasparov's fans had to admit that the once unthinkable might actually be happening. How had it come to this? It was the work of a generation of impassioned computer engineers and programmers that led to Deep Blue. Human chess champion Garry Kasparov was being challenged, really, by other humans. They were arguably as brilliant as Kasparov, and no less disciplined and determined. They passionately believed they could teach their machines to surpass the performance of the human brain. The programming pioneers of the late 1940s knew and respected chess. It was a smart person's game and a worthy challenge. But after all, what a grandmaster did was just look ahead and analyze various possibilities, wasn't it? And computers could be taught to do that, but not easily, and for decades, not very well. Still, by the mid-1980s, computer chess programs began challenging and occasionally beating grandmasters. It remained unclear whether they could ever defeat the world's best. In 1996, after 7 years of research and development, a team at IBM believed they were ready to challenge Garry Kasparov. In Game 1 of 6, Deep Blue eked out its first win against the champion. Kasparov learned fast and won the match decisively. His confident proposal for a rematch in 1997 was immediately accepted by the IBM team. They were learning too. The afternoon of May 11th, 1997. Game 6, the deciding game. Deep Blue challenges Kasparov's brain with an array of 256 processors that can examine 200 million possible moves every second. They call it the brute force approach. Kasparov doesn't try, he can't try, to consider every possible move. He knows from experience what's important, and he relies on the human mind's extraordinary ability to recognize and remember patterns. The patterns of chess experience lived in Deep Blue's software, too. Grandmasters had coached IBM's programmers to deepen Deep Blue's book, its library of what humans knew from experience about how to win. Deep Blue could now play as well as a grandmaster, with all the benefits of hindsight. In the early moves of Game 6, playing by its book of openings, then in the mid-game analyzing millions of possible scenarios by sheer brute force, Deep Blue has led Kasparov into making a poor move. Kasparov is rattled. He defends what he can, but it's clear that the computer will reliably do what he himself would do. And he recognizes that he has already lost. On Deep Blue's 19th move, the champion resigns.
Okay. So that gives you a sense of this man versus machine or human versus machine kind of work that was going on at the time. And pictured here is the cabinet that held Deep Blue. It was actually in the Smithsonian American History Museum because it was such a noteworthy moment. And you notice in the clip that the binary ones and zeros were presented, and they called it the brute force approach that Deep Blue would be running. That would be equivalent to the algorithm method, as we called it, essentially analyzing all possible moves, whereas Kasparov would be using the heuristic method. A couple other thoughts of note. Kasparov had an edge with other humans in that he was a famously demonstrative player. He made a lot of grimaces and sighs. You kind of get that sense from his demeanor in the footage. That would rattle a human player. A computer is not rattled because it doesn't care at all about processing emotion, and so that took away some of Kasparov's intimidation factor. Another interesting thing that happened in the 1997 set of games was that at one point it wasn't really clear what Deep Blue should do, and so it executed what was known as uh, random legal move. It was just programmed to do something that was legal in the game. It didn't matter what. And so it makes this move. And Kasparov was really puzzled by it because it was just a very unusual thing to do. And because it was random, a person wouldn't make that move. And that really got in his head. And so he kind of became his own worst enemy by overthinking what ultimately was just a random occurrence. And so he was, in a sense, tripped up by his vast experience of chess. And you see the differences from the brute force, non-emotional processing power to the expert human, full of emotion and full of self-doubt. And so that was many years ago, and now it's trivial for computers to defeat every human expert at chess. One of the areas that people really excel is in language and semantics. And this has been talked about as maybe a dividing line between people and animals like chimpanzees. Related to behaviorist learning, in the 1960s and 1970s, psychologists around the country were trying to train chimpanzees to either produce artificial sorts of symbols for words. So they would give them a little vocabulary of tokens that they would press buttons or have little plastic tokens. Or in some cases, they tried to teach them actual sign language. And they were somewhat successful in training the chimps to make some some word-based statements, but the chimps would typically just ask for food using one or two symbols or words. It never progressed into the thousands of symbol. It was more like in the hundreds. And it seemed like the chimpanzee was actually learning in very much a behaviorist manner. And so children, on the other hand, are often running with language, just almost inexplicably at age 2. So that was again the problem of B.F. Skinner, was trying to explain that immense productivity and novelty that people are capable of. And that's our semantic memories, those memories that involve world knowledge, and they're tagged by language, and we can think in terms of these whole sets of concepts. And this might be one of those keys, or it was thought to be one of the dividing lines of what makes human cognition different. But there was another really important landmark moment where machines seem to have semantic memories. And this is going back 13 years to IBM's Watson playing the game show Jeopardy! Jeopardy! Is a trivia show, and we'll go ahead and watch some footage of that rather famous instance. What we'll see is the Jeopardy studio, and they have the two top human champions of the day, who were enormously accomplished trivia experts, playing against IBM's Watson computer. Here we go.
A short round of Jeopardy! It's going to be hosted by a member of our Jeopardy! Clue crew. Please welcome Jimmy McGuire. Gentlemen?
Good morning, everybody. Thank you for being here. What do you say we play Jeopardy! Let's get right into the Jeopardy round. These categories: a man, a plane, a canal, Erie, Chicks Dig Me, children's book titles, My Michelle, MC5, and finally, vocabulary. Ken, you're in the first position. Please make a selection.
I've never said this on TV. Chicks Dig Me for 200, please, Jim.
Kathleen Kenyon's excavation of this city mentioned in Joshua showed the walls had been repaired 17 times. Watson.
What is Jericho?
Okay, so Watson gets this right as Jericho. When people play Jeopardy, they have to ring in with a button when they know the answer. Watson doesn't have to do that, and so what they do is Watson will get to answer if it reaches a certain confidence level, which is depicted there. Jericho's at 97%. When it hits that kind of confidence level, Watson is able to answer. That's how they're factoring in the ringing in the button kind of thing.
Go.
Correct.
400, same category.
This mystery author and her archaeologist hubby dug in hopes of finding the lost Syrian city of Urkesh. Watson?
Who is Agatha Christie?
Correct.
And notice that Watson will have its favored answer, and then it shows the second and third best answers that it had. Syria was its third best. It's only at 3%, but that's not even a person. So it's making some mistakes that a person would not make, but it's nonetheless incredibly fast and efficient.
Correct.
Same category, 600.
At the Olduvai Gorge in 1959, she and hubby Lewis found a 1.75 million year old Australopithecus Boise-eyed skull. Watson?
Who is Mary Leakey?
You're right.
800, same category.
Harriet Boyd Hawes was the first woman to discover and excavate a Minoan settlement on this island. Watson?
What is Crete?
Yes.
Let's finish Chicks Dig Me.
At Mount Carmel in Israel, Dorothy Garrod was the first to find this prehistoric human skeleton outside of Europe. Ken?
What is Neanderthal?
You're right.
Let's go to children's book titles for 200.
Marjorie Williams' story of a stuffed toy that comes to life, the blank rabbit. Brad?
What is Velveteen?
You're right.
MC5 for 200, please.
He's worth every penny as Alfred Pennyworth in The Dark Knight. Brad again.
Who is Michael Caine?
You're right.
MC5 for, let's jump down to 800, please.
So the humans are able to score a few times, and that's just where Watson wouldn't have had the same confidence level in its top answer. It's still answering. It's just that they're allowing the humans to take over when that happens.
Edgar Degas' style influenced that of this female American impressionist. Brad.
Who is Mary Cassatt?
Correct.
And MC5 for 1,000.
The film Gigi gave him his signature song, Thank Heaven for Little Girls. Watson.
Who is Maurice Chevalier?
Correct.
Same category, 400.
The parents of this 52nd governor of New York immigrated to the United States from Salerno, Italy. Watson.
Who is Mario Cuomo?
Correct.
So notice what Watson's doing here. The title of the category is MC5. That's going to shape its possible answers. And these are humans, but its best answers are Mario Cuomo, Motorcycle Club, and Marine Corps. This is, again, not thinking the way a person would. MC, if you look up what is the most common abbreviation for MC, it's going to be Motorcycle Club or Marine Corps. And that's why it's producing those. They're not at a high level, but they're mistakes that no person would make, and no one would be thinking that way. Yet it's nonetheless getting the right answers.
Let's finish MC5.
This child star got his first on-screen kiss in My Girl. Ken?
Who's Macaulay Culkin?
Correct.
Children's book titles, 400.
By Judith Viorst, Alexander and the Terrible, Terrible, No Good, Blank, Blank Day. Ken?
What is Very Bad?
Correct.
Book title, 600.
By Dr. Seuss, The Blank Hats of Bartholomew Cubbins. Ken again.
What is 500?
You're right.
So this is one where you can see that Watson's searching the category and it's coming up with other titles by things related to Dr. Seuss, and 500 would be it's a lower confidence level. It's not reaching that threshold, so Ken was able to answer. And so this is where it is kind of getting confused. It's got the right answer. It's just it's muddled up a little bit, and it's doing it in a way that a person wouldn't be.
Book titles, 800.
By Maurice Sendak, In the Blank Kitchen. Ken?
What is Night?
Correct.
Book titles, 1000.
A classic by Crockett Johnson, Harold and the Blank Crayon. Watson.
What is Purple?
So it does get this completion. It's having much harder time with the word completion category. And Maurice Sendak also wrote Where the Wild Things Are. That would never be a completion for a person. So Watson does have a tremendous lookup ability for semantics. And that's really the point of this. The people were ultimately not able to defeat Watson. And that is a landmark moment because it's dealing with what we're good at, which is looking up facts. And the way the Watson cognitive architecture worked is that it would handle both what they called structured data and unstructured data. Structured data would be basically curated by a person, kind of like if it's an author, authors are going to be a human name, and it has that constraint built into the model. Now, unstructured data is going to not be curated by people, and that's things like relations, grammar, and structure. It actually has to be able to interpret what's being said. So it's pretty fantastic that it was able to do that, and pretty impressive. Watson was a service from IBM. They had a consulting service for IBM Watson last decade, 5 to 7 years ago. This was going on, and it was kind of part of that evolution of computing and how it might help us. Okay, so moving on, one of the last holdout skills that a person could still defeat a machine at up until recently was the game of Go. And this is often thought of as a holy grail of human reasoning, a 2,500-year-old strategy game in which players are basically trying to capture territory on this little board here, one playing the white color, one playing the black color. Go players have a history of being really into engineering and computing. People like Einstein, Alan Turing from the textbook, as well as John Nash, of the famous John Nash equilibrium, played Go, and President Benson of UT Dallas is a Go player as well. So one interesting quote from Lee Sedol, who's an expert Go player, is, "There is chess in the Western world, but Go is incomparably more subtle and intellectual." The reason for that is that chess, if you compute the number of possible moves that have are in play at a given moment, there's 20 possible moves on opening for each side. And then after each play, there are 400 possible board configurations. And you can compute a branching factor, and that is the number of moves available per turn. And it turns out to be 35 moves in every chess game. Go, by contrast, has a blank board to start with, and you're adding the little stones to the board. So black plays first. It has 361 possible moves, and white has 360, and it moves on from there. There are almost 130,000 board configurations possible just if the first two moves. So that branching factor comes out to more like 250 moves available per turn. So many, many orders of magnitude higher, and that's what makes Go more complex, both for a human and for a computer. And it had been predicted in 2014 that it would be 10 more years before a Go expert could be defeated by a machine. You can tell from the link that that didn't turn out to be the case. There was a defeat not all that long ago. Let's go ahead and watch a clip on AlphaGo, which had defeated Lee Sedol.
Until recently, computers have been relatively simple. Even the most powerful machines can only carry out the specific tasks they've been programmed for. This limits the scope of what they can do and how we can use them. After all, the real world is messy and unpredictable, and computers aren't good at dealing with that. But what if machines could think like humans? What if software could learn new things by itself? That's been a goal of scientists working on artificial intelligence since the very dawn of the information age, but it's proved a near impossible task. That might be about to change. A piece of software developed in London could just herald the biggest step forward in artificial intelligence and technology for decades. That software is called AlphaGo. It was developed playing simple computer games, and now it's about to take on the best player in the world in a Chinese board game called Go, a game of such complexity and intuition, no machine has ever been able to master it. AlphaGo's creator is the British startup Google DeepMind.
So the game of Go has just two rules, but out of those rules comes profound complexity. There are more possible board configurations in the game of Go than there are atoms in the universe. So really it takes a whole lifetime to master. We're ready now for the sort of next step for us, which is the ultimate challenge to take on one of the world's top Go players. So we've decided to challenge Lee Sedol in a $1 million 5-game match. Lee Sedol is the greatest Go player of the last decade, probably one of the greatest Go players of all time. I describe him as the Roger Federer of Go. And, you know, the press and the excitement there is just huge from the general population because they really love technology and they love Go. Human professional players at the top of the game, you know, they're extremely creative and they'll do unexpected things that your own systems won't do. So we're pretty confident. Our internal tests are saying we should do pretty well. But Lee Sedol also, you know, he's been interviewed by the Korean press and he's very confident of winning. So it's going to be a very interesting match.
Of course, this isn't the first time computers have beaten humans in a board game. But what really marks out AlphaGo from the machines that mastered noughts and crosses in the 1950s and eventually chess in the 1990s is not just its ability to play a much more difficult game. It's the way it plays the game, by learning.
AlphaGo actually learns how to play in quite a human-like manner. So the way we start off training AlphaGo is by showing it 100,000 games that strong amateurs have played that we've downloaded from the internet. And we first initially get AlphaGo to mimic the human player. So we give it a position and we train it to predict the move that the human expert made. But of course, ultimately, we would like AlphaGo to be stronger than human amateurs and compete with the top professionals. So the way we do that is after we take that first version that's learned to mimic human play, we then allow it to play itself 30 million times on our servers. And using reinforcement learning, the system learns to improve itself incrementally through it avoiding its errors and increasing and improving its win rate against older versions of itself. And after all these games, then you end up with a new version that can beat the old version, the original version, around 80–90% of the time.
The computer Deep Blue has tonight triumphed over the world chess champion Garry Kasparov. It's the first time a machine has defeated a reigning world champion in a classical chess match.
Deep Blue Kasparov, after the move C4, has resigned.
This is in many ways a more interesting piece of software than Deep Blue, which was the piece of code that did beat Garry Kasparov back in 1997. Why are people excited at the moment? I think that's because these machine learning techniques have made a little bit of a breakthrough at the sort of lowest level of functionality that's really important for AI, which is perception. So being able to take raw data, large quantities of raw data, such as images or sounds, and to be able to do the basic processing and recognize what's there.
Key to understanding why AlphaGo could be a much bigger breakthrough than Deep Blue is to see just how differently the two machines work. Deep Blue was programmed to recognize the value of each piece on the chessboard. It then used raw computing power to search every possibility to work out which one was best. It's a bit like trying every password combination until the safe unlocks. But ask Deep Blue to do anything other than play chess, like even play a much simpler game, and it just won't know where to start. AlphaGo is different. Like a human, it can't measure all the possibilities in Go. There are just too many. Instead, AlphaGo teaches itself to play the game by watching thousands of others, playing matches against itself, and learning from its own mistakes. When historians come to write about the 21st century, I believe this match will be seen as a pivotal moment in our relationship with technology, because as DeepMind software shows, we may be entering an age of thinking machines, general artificial intelligence, capable of carrying out a huge number of tasks currently done by humans. And whether or not DeepMind wins the game, it's likely that intelligent machines are going to have a profound impact on the world around us.
Okay, so this was really another important moment. And let's jump back into the slides. In 2016, Google's AlphaGo did win the match. So it won games 1, 2, 3, and 5 against Lee Sedol. And there was real money on the line here. It was a $1 million match, 5-game match in Seoul, Korea. And I think the money went to charity. I'm pretty sure of that. And very much like the Kasparov loss from decades earlier, this was sort of just, wow, machine learning has evolved to that level where it's able to, defeat the top person. So that was only 2 years after the prediction that it would be another decade. And so that's how fast computing has evolved over time. So just taking stock of those sort of human versus machine, the timeline, ENIAC was one of the first very large computers that was post-World War II. It took till 1981, so almost 40 years before personal computers became common in homes and offices. Then an algorithm called Chinook had won at checkers. In the late 80s, Deep Blue wins at chess in 1997. Gradually, Watson comes about with that semantic search capability in 2011, and by 2016, AlphaGo defeats a person at Go. There's not much else to do as far as human versus computer games. The algorithms have won at this point. The question is really what's next, and this gets into these terms weak versus strong AI. When people talk about weak AI, that's the kind of AI that AlphaGo would be, or even Deep Blue, where it's for a particular task. It's going to be specialized to solve the task, but then it doesn't have the general capabilities of being an overall problem solver. That would be strong AI, which would be like a general problem solver, an AI that's very human-like and really indistinguishable from a human. You could play checkers against it. You could play chess, you could play Go, you could ask it to compose a poem, and it would do all of those things just the way a person would. And I think now with the large language models that exist, we are starting to see something that resembles that. You can ask a large language model, um, Bard, for example, or chat one of the ChatGPT iterations questions, and it does give human-like answers. So that semantic search that we saw with something like Watson 13 or 14 years ago, and then moving into modern eras, the semantic search capability is far more impressive. And so we carry with us this library of human knowledge within our pockets every day. And it's just worth reflecting on the history here. So, for most of human history, it was not possible to even read. Most people lack that ability, and there just weren't many books around, for thousands of years. In relatively recent times, like last century, you have libraries in which the public can access a lot of semantic information, but they have to go to a physical building, find something themselves laboriously on index cards, then go get a physical set of paper and then look the darn thing up themselves. It's immensely costly in terms of time and effort. We do outsource some of this stuff just into our brains. We don't have to actively do the search. Our temporal lobes are highlighted in red, and that's an area of the brain that is involved in a lot of our semantic networks. So when you think about dogs, there are some high probability things that come to mind, like golden retrievers and German shepherds and chihuahuas, and the look of the dog, the fact that it has hair, the rough size, all that comes along immediately when the concept of dog comes up. And then we can embellish that category over time, but we'll ultimately have to look up other things that we can't personally experience. And we now do that with algorithms. So search engines, probably Google being the most influential. When Google came out with their original algorithms over 20 years ago, it was really revolutionary. They were just simply a better search engine that was giving you more of what you wanted quicker. And now we're to the point where, Gmail will complete sentences for you, and large language models can do remarkable things in terms of allowing us to learn. So we're outsourcing more and more of our knowledge to look it up via device. And you'll notice that people don't really have urban legends anymore. The urban legends were these, sort of false notions that would come about, and there was really no way to fact check it. So, that's absolutely not the case now. It's extremely easy to fact check things. However, modern technology leaves us open to misinformation or disinformation and being misled in large ways. And that, of course, needs to be corrected. So just to wrap up here, we're not going to solve that one today. Cognitive psychology had developed after behaviorism, really after a period where it was no longer possible to explain things like the complexity of human language or semantics or memory systems. And it stepped in with this information processing approach, likening the mind to a computer system, all the while actual computers were being developed to process information in tandem. And over the years, there were these clashes pitting the human mind against the silicon-based mind, and over time, computers have been able to outstrip our capabilities on things like chess or trivia games like Jeopardy or Go, and there really aren't many more frontiers for AI to conquer people on, except for the general capability of purposeful behavior, which we still are able to, run the show there, at least for now. So I'm going to go ahead and wrap up here. And the real question, I think, for the future is how intelligent behavior can be organized where a person really teams up with a computer. We do this all the time with our smartphones, but even more efficiencies and accuracy might be possible, and we have that to look forward to. I hope you've enjoyed this lecture.